So for my senior thesis in physics, I set out to build a high-resolution spectrometer. To first understand the spectrometer, you have to understand spectroscopy, which is the study of the interaction between matter and light. All of matter is made up of an uncountable number of atoms, so understanding the interactions between these atoms govern the interactions between matter itself. So we can't directly view what's going on in atoms just as a result of how small they are, so we have to find indirect methods with which to study what's going on in these atoms, and light provides a very convenient tool to study them. So as atoms fall from one higher energy level to a lower energy level, they release a photon of light that has energy that's proportional to the difference between the two levels. And if we measure the color of the photon, we can easily find out the wavelength of that light of that photon, and as a result, the energy of that photon. So if we take a sample of light and unpack all of the underlying wavelengths within that light, we can easily find all of the different energy level transitions that are going on in an atom that that sample of light represents. So this is important because different atoms obviously have different atomic structures. And as a result of the different atomic structures, you just have a variety of energy levels that an atom can take on. So by studying the different wavelengths of light that an atom produces when we excite it, we can understand the different energy levels that are occurring. And as a result, we can match those to different elements. And with a high resolution, we can actually match those to different isotopes within the same element. So spectrometers essentially are a machine that takes a sample of light and unpacks it into its component wavelengths and then measures each of the components of those wavelengths. So the central component to all spectrometers are a dispersive element. We can see an example of a dispersive element in the top left of the slide there, called a diffraction grating. So this dispersive element breaks up light, or reflects light at an angle depending on the wavelength of light in that what is called spectral line, which is the individual color of that light. And by measuring the angle between the first incident sample of light and then the reflected wavelength of light, we can find the actual energy that's in that light. And through putting together all of the spectral lines in a sample of light, we can put together the picture of all of the energy transitions that are going on in the atom, which is called the spectrum. So I set out to build an Ebert spectrometer, which is a low-cost design of a spectrometer because it only has two optical instruments. But as a result of the fewer number of optical instruments, it requires a significant amount of alignment and an electronical and mechanical control system to tie together all the optical components with the actual measurements of the light. The theoretical top-down design of my Ebert is on the top right, and then below that is an actual view of the spectrometer from the side. So I set out to build one that could distinguish between two different isotopes of hydrogen, which is a difference of 1 × 10⁻⁴ degrees. And I was lucky enough to build a spectrometer that wasn't quite there, but did 6 × 10⁻⁴ degrees between each spectral line. And that's high enough for a wide variety of physics research. Thank you.